You are sitting where you are now. The walls of your room contain you. Your body feels familiar, bounded, predictable. The clock ticks with the constancy you expect. Outside, the sky appears stable, the stars distant and unchanging. You trust these perceptions because they are immediate. You trust the measurements humans have made over centuries because they are precise. You trust the logic of mathematics because it maps onto reality with uncanny reliability. And yet, somewhere far beyond your room, beyond the reach of your senses, there exists a planet so large, so massive, that the very concept of habitability seems incompatible with its size. Its mass should crush any atmosphere. Its gravity should prevent water from settling in liquid form. Its star should make it inhospitable by any conventional standard. And yet, observation shows it is not only possible that life-supporting conditions exist there, but that the planet may host them on a scale we have never encountered. This is not speculation. This is the direct implication of precise measurements of mass, radius, and orbital behavior. Every piece of data that points to this world's existence has been verified. Every contradiction between expectation and observation is grounded in real numbers, confirmed light curves, and spectral signatures. The question then is simple and unresolvable. How can a world so vast still be, in some sense, familiar to life as we know it? And if it can exist, what does that imply about everything you think you understand about planets, stars, and the limits of physical possibility? The planet that should not be. You assume that planetary size is bounded by physics. Above a certain mass, pressure flattens the interior, gravity overwhelms the surface, and no conditions compatible with liquid water or stable atmosphere could exist. Yet the data shows a planet exceeding these limits, orbiting a star in a zone where life could, in theory, persist. From the first measurements, its radius was astonishing. The transit depth observed in the light curve suggested a planet that dwarfed any known terrestrial world. Instruments designed to detect small variations in stellar brightness recorded a dimming far greater than Earth's analogs. Yet the pattern repeated with consistent periodicity, confirming that this was not an artifact of observation. Radial velocity data, which measures the gravitational influence of the planet on its star, corroborated the mass estimates, producing values far beyond those considered compatible with habitability. You might expect that a planet of such mass would collapse into a dense, unrecognizable object, its interior compressed to an almost metallic state. Conventional models predict that above a certain threshold, gravitational pressure would prevent the formation of stable oceans or even a stratified atmosphere. Gas would be forced into the lower layers, lighter elements would escape, and any semblance of surface conditions suitable for life would be erased. Yet the spectral analysis from the planet's atmosphere shows distinct chemical signatures, including compounds that could suggest the presence of liquid water, a condition seemingly impossible under such extreme gravity. The contradiction is not subtle. By standard planetary physics, the planet should either have become a gas giant or lost its ability to retain an atmosphere entirely. Its density is unusually low for a world of its size. The mass, though enormous, is distributed in a way that produces surface conditions far less extreme than expected. For you, observing this through a telescope or reading the numerical reports, it feels as if a law of physics has been locally suspended, a rare exception that your equations do not predict. Yet every measurement is verified. Multiple transits, independent instruments, and repeated spectroscopic analyses converge on the same conclusion. There is no error large enough to reconcile this planet with conventional expectation. The more precise your observations become, the clearer the anomaly appears. The planet's size, mass, and orbit are real. Its capacity to sustain an environment marginally compatible with life is implied by the data. Consider the implications of its gravitational field. You would expect tides so intense that oceans, if they existed, would be torn apart. You would expect atmospheric convection to break down into turbulent layers, destroying stability. Yet models of the planet's energy balance, when constrained by observation, suggest a system that is, paradoxically, both massive and stable. The mechanisms for such stability are unclear. Thermal gradients, magnetic interactions, and rotational inertia all contribute, yet none alone explain the apparent balance. The planet's orbit compounds the puzzle. It lies within a region often called the Habitable Zone, yet the star it orbits is more luminous than the sun. The radiation it receives should drive runaway heating, yet equilibrium is maintained. Any slight perturbation in orbital eccentricity or stellar output should have catastrophic consequences, yet the planet persists, a slow-moving anomaly against the backdrop of predictable astrophysics. You are forced to confront the limits of your assumptions. Planetary mass, atmospheric retention, surface conditions. These are not merely parameters to be measured. They are constraints derived from centuries of observation, applied uniformly across countless worlds. And here is a counterexample so extreme that it challenges the universality of those constraints. The planet is a data point, but it is also a warning. The universe permits structures that stretch your understanding, that expand the range of what is physically possible without breaking the observational record. Its existence does not comfort you. It does not hint at hidden knowledge or invite speculation in familiar forms. It simply is, and in being so, it undermines assumptions you relied upon as immutable. The planet that should not exist does exist, and its reality is as precise and unambiguous as any measurement humans have ever made. Your task in observing it is not to rationalize it. It is to recognize that the universe quietly allows phenomena that contradict expectation, that challenge intuition, and that leave you standing in your room, feeling the gravity of what is real, and knowing that some possibilities, however improbable, are already here. The gravity paradox. You experience gravity as uniform and predictable. A planet's gravity, increasing with mass, should distort structures and fluids in ways that prevent conventional life. On this planet, calculations suggest surface gravity stronger than anything on Earth, yet the spectra indicate the presence of atmospheric layers that remain stable and differentiated. Gravity, as you have measured it on Earth, is a simple constant, familiar, unyielding. It dictates the weight of every object, the fall of every drop, the flow of every river. You expect these effects to scale linearly with mass, and beyond a certain point, non-linearly with catastrophic consequences. Yet on this planet, the expected distortions do not manifest in ways your intuition predicts. Spectral signatures of gases reveal distinct bands. Layers of hydrogen, nitrogen, water vapor, and trace compounds that remain separate, showing no evidence of the violent mixing that extreme gravity would imply. Your mental model suggests that such strong gravity should compress the lower atmosphere, raising pressure to levels that would crush molecular structures or collapse the stratification into a dense, homogeneous envelope. The top layers should be thin, almost negligible, while the bottom layers should reach extremes of pressure exceeding what any life-sustaining chemistry could tolerate. Yet, transit spectroscopy shows absorption features that indicate stable, distinct layers from surface to upper atmosphere. This chemical gradients are consistent with equilibrium processes familiar to smaller worlds, suggesting that the planet has found a way to maintain differentiation despite overwhelming force. This paradox is reinforced by the planet's size and mass. Gravity at the surface, as inferred from radius and mass calculations, should produce pressures far exceeding those on Earth. Oceans, if they exist, should be compressed into shallow, high-pressure layers, incapable of sustaining convection currents necessary for climate moderation. Solid crusts should be distorted, potentially fractured under the strain of immense weight. Yet observations show nothing in the spectral data indicating global collapse or chaotic disruption. The gases, the water vapor, even potential aerosols, all remain structured, layered, and behaving in ways consistent with a more modest gravitational environment. You notice the quiet, insistent pattern in the data. The planet's rotation and orbital parameters combine with its mass to produce gravity strong enough to challenge assumptions about habitability. Yet the measured atmospheric properties suggest conditions are stable, at least in the sense that the layers are not violently mixing. The planet's environment is extreme, but not catastrophic. The forces that should destroy order are instead contained, producing a system that is both massive and internally coherent. The implications extend beyond planetary science. If gravity can be this intense and still permit atmospheric differentiation, then your understanding of physical limits is incomplete. Fluid dynamics, convection, chemical stratification, concepts grounded in centuries of terrestrial observation, may not scale in the way you expected. The universe permits stable structures at scales you assumed would be impossible. Measurements, not speculation, reveal the contradiction. The planet's gravity is extraordinary, yet the atmospheric system remains surprisingly familiar in behavior. The paradox deepens when considering the interplay with temperature and heat transport. Strong gravity should compress gases and increase thermal conductivity. Yet the thermal spectrum suggests energy distribution occurs in patterns not fully explained by current models. Heat is transported efficiently, but without the turbulent chaos you would predict. The planet demonstrates that gravitational extremes do not necessarily entail instability, but instead can coexist with orderly stratification, a subtle, almost imperceptible violation of expectation. You are confronted by the quiet, uncompromising lesson of observation. Gravity, one of the most basic forces you trust, behaves predictably in calculation, yet produces results in nature that confound intuition. The planet is a reminder that the physical world contains regimes where your assumptions, even those derived from the most reliable measurements, do not fully apply. It is both familiar and alien, massive yet structured, a place where order persists under forces that should destroy it. The surface gravity you imagine should be oppressive, perhaps lethal, yet the atmosphere itself seems to resist collapse. Layers remain distinct. Chemical gradients endure. Light bends across the horizon in ways consistent with stable density profiles. You are left with the realization that gravity, the force you feel constantly and intuitively, can exist at extremes without erasing structure. The paradox is quiet but persistent, and it lingers in every measurement you examine, in every spectral line, in every calculation that cannot reconcile force with stability. Measuring mass and radius. Your intuition tells you mass and radius scale together in simple ways. Transit and radial velocity measurements, however, reveal a world whose density is far lower than expected. It is enormous without being uninhabitable, a violation of the scaling laws you take for granted. On Earth and in our solar system, planets follow a clear pattern. As radius increases, mass increases proportionally, and density follows predictable curves. Small terrestrial planets have high densities. Gas giants have low densities. These relationships emerge from gravity, material composition, and compressibility. They are confirmed across dozens of worlds, measured with precision through decades of observation. Yet this planet does not conform. Its radius is immense, many times that of Earth, but its density is unusually low. The mass is large, yes, but not so large that surface conditions become hostile. By the standards of planetary physics, this is a contradiction encoded directly in the data. The methods that reveal this paradox are robust. The transit method measures the slight dimming of starlight as a planet passes in front of its star. The depth of the transit corresponds directly to the planet's radius. Radial velocity, the measurement of the star's wobble due to gravitational pull, gives mass. Both methods have independent uncertainties, yet both converge on numbers that cannot be reconciled with traditional scaling laws. The planet's volume is vast, its mass not overwhelming, and yet its surface appears, at least in part, hospitable. You would expect that any planet of such size must be dense to maintain structural integrity, or conversely, that a low-density world must be predominantly gaseous, incapable of sustaining surface conditions familiar to terrestrial life. Yet here, the planet is enormous and low density, implying an internal structure that challenges your assumptions. Models of interior composition suggest a mixture of silicates and volatiles, spread over a radius far larger than any Earth-like analog. Compression under gravity should produce pressures and temperatures that make liquid water unstable. Yet spectral analysis and thermal models indicate conditions that allow it. Even small variations in measurement amplify the strangeness. A slightly higher mass would predict crushing gravity. A slightly smaller radius would suggest uninhabitable density. Yet repeated observations across different telescopes and instruments confirm the same combination. Size enormous, mass moderate, and conditions unexpectedly compatible with habitability. The precision of this data leaves no room for convenient error. the anomaly is real and unavoidable. The consequences extend beyond this single planet. If mass and radius can decouple in this way, then our models for planetary formation may be incomplete. The processes by which planets accrete material, retain atmospheres, and distribute mass internally are underdetermined by current theory. The universe allows planets that defy scaling expectations, suggesting that the range of physical possibility is broader than your intuition permits. What you thought were hard limits, size, mass, density, are in fact contingent, observable only through measurement. You notice the subtle implications in the data. Large radius with moderate mass means gravity is strong but not overwhelming. Surface pressure is high, yet not fatal. Atmospheres remain layered. Oceans could persist. The planet exists in a regime that your models treat as improbable, yet observation shows it is realized. The laws of physics are intact, but your mental map of where habitable planets should lie is incomplete. The planet also forces you to reconsider the meaning of density itself. What does it mean for a planet to be light at a colossal size? The interior must be structured to support the outer layers, yet remain diffuse enough to avoid catastrophic compression. Thermal and mechanical energy are distributed in ways that are counterintuitive, yet observable. Every number in the data set points to an anomaly that is quiet but insistent. The physical world is capable of maintaining improbable equilibrium. Ultimately, the measurement of mass and radius is not merely descriptive, it is confrontational. It presents a world whose size suggests uninhabitability, whose mass suggests crushing gravity, and whose density implies contradiction. And yet, every observation confirms its existence. You are left to hold numbers in your mind that do not conform to expectation, to witness through data a planet that challenges the very assumptions you rely upon when imagining worlds beyond your own. The star. It orbits. Stars radiate energy in predictable ways. You expect intense heat and radiation from a star of this type to sterilize nearby planets. Yet this planet's orbit keeps it within a narrow window of flux that could allow liquid water, implying a delicate balance measured precisely by instruments you rely on every day. On the scale of stellar physics, the star appears ordinary. Its luminosity, temperature, and spectral type are consistent with hundreds of other stars you have catalogued. From a distance, it behaves exactly as your models predict, radiating energy in a consistent spectrum, following well-understood nuclear fusion processes. Yet the planet's position relative to this star is exceptional. The orbital radius situates it in the so-called habitable zone, where the energy received is sufficient to maintain surface temperatures compatible with liquid water, yet not so great as to trigger runaway heating. The precision of this placement is measurable. Small deviations inward or outward would render the planet inhospitable. You consider the forces at play. Orbital mechanics dictate that a planet cannot remain in a perfect orbit indefinitely. Gravitational interactions with other bodies, stellar mass loss, and tidal forces all perturb motion over time. Yet measurements of this planet's period, eccentricity, and inclination reveal an orbit stable enough to maintain the delicate balance of energy flux over millions of years. The combination of stellar output and orbital configuration produces a climate regime that, by every known calculation, should be improbable for a planet of this size and mass. The narrowness of the flux window is striking. Observations of the star's radiation, taken over decades, reveal minor variability, flares, spots, and pulsations that affect the planet's incoming energy. Yet the planet's atmosphere and potential hydrosphere absorb and redistribute energy in a manner consistent with long-term equilibrium. Thermal infrared measurements suggest temperatures that, while extreme, remain within the bounds for stable liquid reservoirs. The star's behavior and the planet's orbital characteristics interact in a way that is both precise and delicate, as if nature allows for a narrow path in which the improbable becomes real. You examine the implications for habitability. The star is not a gentle sun like Earth's. It is larger, brighter, and more luminous. The planet is larger, more massive, and with higher gravity. Each parameter, taken individually, would be sufficient to preclude life. Combined, they create a system balanced on a knife's edge. The planet does not merely exist in this environment. It survives within it, maintaining conditions that are both extraordinary and observable. The star also influences atmospheric dynamics. Radiative heating drives circulation patterns, convection currents, and weather systems. In ordinary circumstances, intense flux from a bright star would produce extreme instability in a planetary atmosphere. Yet the spectral analysis of this world indicates stable stratification and a retention of gases across multiple layers. Light and heat are distributed in ways that maintain the integrity of the system, a subtle and ongoing defiance of what you expect from standard models. Even small perturbations magnify the paradox. A slight eccentricity in the orbit would push the planet too close to the star, increasing radiation and triggering potential atmospheric loss. A slightly higher luminosity would boil surface water. Yet the planet endures, suggesting either an unusual damping mechanism, an outcome of initial conditions so precise that you can only recognize it as measurement. It is an observed balance, not an assumption, and it is remarkably exact. You are forced to confront the quiet implications. The star behaves predictably, and the planet behaves predictably, yet their interaction produces a system that should, in theory, be fragile, yet is observable, stable, and capable of sustaining familiar physical processes. It is a system that challenges your understanding of probability, equilibrium, and planetary habitability. What seems impossible in theory exists in reality, quietly, without dramatization, confirmed only by measurement and observation. In every photon you capture, in every spectral line, and in every calculated orbit, the paradox persists. A planet this large, under a star this bright, should not maintain surface conditions suitable for water or potential life. And yet, it does. The star it orbits, precise in every measurable characteristic, permits an environment that defies expectation. A silent, measured contradiction that forces you to reconsider the limits of planetary possibility. Atmospheres under pressure. You assume atmospheric layers. Collapse under extreme gravity, yet spectral analysis shows distinct gaseous layers with trace compounds like water vapor and carbon dioxide remaining separated rather than homogenized. The mechanics of this layering defy the simplest thermodynamic expectations. On planets with familiar gravity, gases stratify according to density, temperature, and pressure gradients. Heavier molecules sink, lighter molecules rise. Convection, turbulence, and diffusion mix the layers over time, producing predictable vertical profiles. In massive planets, you expect these processes to amplify. Extreme gravity should compress the lower atmosphere, creating pressures so high that molecular motion becomes constrained. You would predict uniformity, a homogenization of gases that erases subtle chemical distinctions. Yet the spectra from this planet reveal discrete bands, each maintaining its chemical identity across layers. The data comes from multiple sources. Transit spectroscopy shows absorption features at different wavelengths corresponding to specific compounds. Infrared observations reveal thermal structure, indicating that temperatures decrease with altitude in a manner consistent with a layered atmosphere. Even minor constituents, such as water vapor and carbon dioxide, show distinct, stable distributions, as if the atmosphere itself resists collapse. No known terrestrial mechanism accounts for this persistence under the planet's gravitational regime. Consider the implications for fluid mechanics. Gravity should drive convection so strong that gases mix aggressively, smoothing out density and chemical gradients. Instead, the upper atmosphere shows minimal turbulence. Thermal energy is transported efficiently without destroying stratification. There is a quiet equilibrium sustained by mechanisms that your models predict should fail under extreme mass. The planet demonstrates that atmospheres can exist in a state of high pressure without succumbing to the uniformity you would expect. This layering has further consequences for surface conditions. Atmospheric pressure at the lower layers is extremely high, yet not enough to prevent the existence of liquid reservoirs. Convection is sufficient to redistribute heat, preventing catastrophic hotspots, yet gentle enough to avoid erasing chemical stratification. Light passing through the atmosphere bends predictably, indicating that density gradients are present and stable. The planet's air behaves simultaneously as a dense, high-pressure environment and as a medium capable of maintaining the subtle structures necessary for potential habitability. You begin to see a pattern emerging. Every observation that should indicate collapse, mixing, or destruction instead reveals persistence. The atmosphere is layered, differentiated, and orderly. Minor fluctuations in temperature or composition do not disrupt this structure, implying feedback mechanisms or structural balances that are subtle yet measurable. The planet has found a way to resist the intuitive consequences of its own gravity. Even extreme events, such as minor stellar flares, do not appear to destabilize the layers. Radiative energy is absorbed and redistributed in a way that preserves chemical gradients. The result is an atmosphere that is, in every measurable sense, stable under conditions where instability should dominate. This is not a speculative property. It is a fact derived from repeated, independent observations. Every spectral line, every thermal signature, and every transit measurement confirms that the atmosphere exists in a state of improbable equilibrium. The paradox extends to your understanding of physical limits. Atmospheric physics, thermodynamics, and convection models all suggest that this system should not exist, yet it does. Observation, measurement, and analysis show a planet where high gravity does not imply homogenization, where molecular stratification persists, and where pressure does not erase structure. Your assumptions about what is possible under extreme planetary conditions are challenged by quiet, unyielding data. Ultimately, the atmosphere is a testament to the universe's subtlety. You expect destruction under force. You expect collapse under pressure. Instead, you find persistence, layering, and stability. The planet under observation demonstrates that the natural world contains regimes of behavior that defy intuition while remaining fully measurable, fully observable, and fully real. It is an atmosphere under pressure, yet unbroken. The temperature distribution. Thermal models predict that extreme mass and proximity to a star should create runaway greenhouse or icehouse effects. Yet infrared measurements indicate temperatures within a range compatible with surface liquid, water, suggesting a stabilizing mechanism that is not yet fully understood. On planets of comparable size and stellar exposure, energy balance calculations indicate extremes. Incoming radiation from the star heats the surface and atmosphere, while infrared emission cools the planet. The interplay of mass, atmospheric density, and radiation often results in runaway processes. Either a greenhouse effect where heat accumulates uncontrollably, or an icehouse scenario where heat is lost faster than it is replenished. In this planet, neither outcome occurs. Infrared spectra show temperatures distributed across the surface and atmosphere in patterns that are surprisingly moderate given the expected extremes. You examine the data in detail. The equatorial regions, measured through phase curve analysis, are warmer, as expected, but not catastrophically so. Polar regions remain cooler, yet the gradient is far shallower than standard models predict. Vertical temperature profiles, inferred from molecular absorption lines, indicate a troposphere and stratosphere behaving in ways consistent with convective heat redistribution. The planet is massive, and its gravity should amplify any thermal extremes, yet observations suggest a system of thermal moderation operating over thousands of kilometers. The planet's rotation and axial tilt are critical factors. On smaller planets, rapid rotation spreads heat, while slow rotation allows extremes. Here, the rotation period is moderate, yet sufficient to distribute energy evenly across the surface. Thermal inertia from the dense atmosphere further smooths fluctuations, damping peaks and valleys. You recognize that these processes interact in ways that are predictable in principle. Yet the precision of the resulting equilibrium is surprising. The planet does not experience catastrophic swings. It achieves a temperature range narrow enough to permit stable liquid reservoirs. Consider the role of the star. Its radiation is more intense than the sun's, yet orbital dynamics keep the planet within a narrow flux window. Stellar variability, flares, sunspots, minor luminosity shifts, introduces perturbations. But the planet's atmosphere appears to buffer these changes. Convection, radiation transport, and molecular absorption work together to absorb excess energy, redistribute it, and release it slowly. The result is a stabilizing effect that is observable but not fully explained by conventional models. This temperature distribution also has implications for habitability. Oceans or other surface liquids require specific ranges to remain stable. Too hot, and evaporation dominates. Too cold, and freezing locks the water in place. The measurements indicate a range that would allow persistence of liquid over geological timescales. In other words, the planet achieves equilibrium in a regime that conventional thermal physics would predict should be hostile. The observation is unambiguous. The planet's thermal system is both extreme in scale and moderate in outcome. You are forced to reconsider assumptions about mass, gravity, and radiative physics. Extreme mass should amplify heating, yet it does not produce catastrophic greenhouse effects. Proximity to the star should increase energy input, yet the planet maintains moderation. The stabilizing mechanisms are subtle, distributed across the atmosphere and interior, and measurable through infrared spectra. Yet they are not fully accounted for in standard planetary climate models. Even minor perturbations, seasonal variations, orbital eccentricity, stellar flares, do not appear to disrupt the overall balance. Energy is absorbed, redistributed, and emitted in a continuous, almost imperceptible feedback loop. The planet's temperature distribution is stable, finely tuned, and counterintuitive. Observation, not theory, dictates that such a system exists, forcing you to accept that extreme planetary conditions can coexist with equilibrium in ways that defy simple expectation. Ultimately, the temperature distribution illustrates a quiet tension between observation and prediction. You expect extremes, but find moderation. You expect chaos, but observe order. Measurements confirm a system that should not exist, yet does, providing a glimpse into physical regimes where the rules are subtle, the outcomes precise, and the universe quietly permits what intuition deems improbable. Rotation and day length. You understand a planet's rotation as a simple function of angular momentum. Observations reveal a rotation period that would be impossible if internal friction and tidal forces were considered normally. Yet it spins neither too slowly nor too fast, preserving the potential for climate stability. Rotation is a fundamental property of planets, determined by the angular momentum inherited during formation and modified over time by interactions with moons, neighboring planets, and the host star. In massive planets, internal friction from viscous mantles and tidal forces should produce gradual slowing, potentially leading to tidal locking. For a world of this size, your models predict extremes. Either a near-complete lock with the star, producing permanent day and night hemispheres, or a chaotic, irregular spin destabilized by internal dissipation. Neither extreme is observed here. Measurements indicate a rotation period comparable to Earth's, neither so long as to produce stagnant hemispheres, nor so short as to generate destructive equatorial winds. The planet's day-night cycle is surprisingly moderate, a rhythm that allows atmospheric circulation to distribute heat effectively, preventing runaway thermal gradients. The observation is precise. Light curves and Doppler spectroscopy confirm consistent rotation across multiple orbits, repeated independently by separate instruments. The data leaves no room for error. The rotation period is real, yet it challenges the expectations imposed by the planet's mass and internal structure. You consider the forces that would normally alter rotation: tidal interactions with the star, gravitational perturbations from other planets, and friction within the dense interior all act to change spin over time. For a planet of this size and mass, these effects should be amplified, yet they appear balanced. The current rotation period suggests either an initial condition of extreme specificity or a stabilizing mechanism that is not captured by conventional models. In either case, the result is a rotation finely tuned for the maintenance of climate stability. The rotation also interacts with the atmosphere. On rapidly spinning planets, Coriolis forces create turbulent wind patterns, while slow rotation reduces circulation, producing thermal extremes between poles and equator. Here, the rotation period supports a moderate climate regime, allowing heat to move across the surface without producing destructive storms or stagnant regions. Infrared measurements and atmospheric modeling indicate that energy is redistributed efficiently, preventing both overheating in the day and freezing at night. The planet achieves an equilibrium in which rotation, gravity, and atmospheric dynamics coexist without catastrophic imbalance. You notice the subtle implications for habitability. Liquid water requires not only temperature stability, but also dynamic equilibrium in circulation. A day that is too long or too short could destabilize climate patterns, yet this planet's period maintains a rhythm conducive to persistent liquid reservoirs. Rotation, gravity, and stellar energy all interact in precise ways, producing a system in which extreme physical parameters nonetheless permit familiar thermodynamic behavior. Even small perturbations, such as gravitational nudges or minor variations in internal viscosity, do not appear to disrupt the rotation. The spin remains steady over observational timescales, suggesting that the planet exists in a dynamically stable configuration that is improbable but measurable. Angular momentum is conserved, yet distributed in a way that preserves surface habitability. Ultimately, the rotation and day-length force you to confront a quiet paradox. Extreme size and mass should preclude stable spin, yet observation confirms it. The planet demonstrates that physical constraints you consider absolute, tidal friction, internal viscosity, gravitational interactions, can coexist with unexpected stability. Rotation, like gravity and temperature, behaves in ways that defy simple expectation while remaining consistent with measurement. In observing this planet, you recognize that spin, often taken for granted as a consequence of formation, is in fact another subtle example of the universe permitting improbable equilibrium. The day passes, the atmosphere circulates, and liquid reservoirs persist. Observation confirms what theory would doubt. The planet rotates in defiance of expectation, silently preserving conditions that should be impossible. Tidal interactions. You expect tidal forces between large planets and their stars to generate destructive stresses. Here, tidal locking is partial, producing enough heat for geological activity without destabilizing the crust. The precision of this balance is apparent in the orbital mechanics, as recorded through years of observation. Tides arise from differential gravitational forces. The star pulls more strongly on the near side of the planet than the far side. On Earth, these forces produce oceans that rise and fall daily, subtle but measurable. On a massive planet, the effect is far more extreme. The gravitational differential should flex the crust, generate internal friction, and create heat far beyond levels sustainable without structural damage. Yet this planet exhibits a delicate partial tidal lock. The rotation has slowed relative to its orbital period, but not to the point of complete synchronization. This partial locking is revealed in the precise measurements of transit timing and stellar wobble. Repeated observations confirm that the planet's rotation period is nearly, but not exactly, matched to its orbit. The result is a consistent pattern of tidal flexing that produces internal heating without triggering catastrophic deformation. The crust remains intact, and surface features, inferred indirectly from thermal emission and density modeling, appear coherent rather than fractured. What would normally be destructive here is transformed into a stabilizing mechanism, sustaining conditions favorable for surface processes and possibly subsurface activity. You consider the energy involved. Tidal forces on a planet of this mass generate heat at magnitudes far exceeding Earth's geothermal output. This energy, in turn, drives convection within the mantle, facilitating geological activity such as volcanism and tectonics. Ordinarily, such intense activity could destabilize the crust, release excessive gas, or disrupt the atmosphere. Instead, the heat is delivered at a rate moderated by the orbital configuration. Partial tidal locking distributes stresses across the interior in a precise balance that allows continuous, predictable energy transfer. The planetary system is therefore finely tuned in a manner that you can measure, but that is difficult to predict from first principles. Small deviations in orbital eccentricity or inclination would amplify tidal heating to destructive levels. Slightly faster rotation or closer proximity to the star would generate excessive internal stress. Yet this planet maintains a dynamic equilibrium. Tidal energy is sufficient to drive internal processes, yet insufficient to cause structural collapse. Observation shows a world operating at the edge of physical limits, a balance that is improbable but real. Tidal interactions also influence the atmosphere. Internal heating affects surface temperature distribution, contributing to the moderation of climate extremes. The slow flexing of the crust facilitates volcanism and outgassing, which replenishes atmospheric components, while the ocean, if present, experiences tides that circulate energy without destabilizing layers. The planet's geology and atmosphere are therefore linked through tidal mechanics in ways that allow order to persist under extreme forces. You are confronted by the quiet implications. Tidal interactions, which are often destructive in massive systems, here become a mechanism of stability. The planet exists in a regime where forces that should threaten habitability instead support it. Internal heating, surface stability, and orbital mechanics align precisely, creating conditions that are both extreme and sustainable. Each measurement, from transit timing to radial velocity, confirms this improbable coherence. Even perturbations from minor moons or neighboring planets appear insufficient to destabilize the system. The planet's partial tidal lock remains steady over observational timescales. The energy from tidal flexing is sufficient to maintain geological and atmospheric processes, but restrained enough to preserve the crust and layered atmosphere. This is not speculative. It is observable. Ultimately, tidal interactions reveal another subtle paradox of this world. Forces that should be catastrophic are, instead, contained. The planet demonstrates that the universe allows equilibrium to emerge in extreme environments, where internal and external dynamics operate with improbable precision. It is a world defined by measured balance, where destructive energy is transformed into order, quietly challenging every expectation about tidal physics and planetary limits. The implications for habitability. Habitability is usually limited by planetary size, atmosphere, and stellar energy. This planet meets the criteria in every measurable dimension, challenging assumptions that life is constrained to Earth-sized or smaller worlds. On familiar planets, habitability is constrained by factors that are relatively straightforward. Gravity must be moderate. Atmospheric pressure must allow liquid water. And stellar energy must not overwhelm or freeze the surface. In larger planets, these constraints intensify. Gravity is expected to crush potential ecosystems. Atmospheres are expected to collapse or become unbreathable, and heat from the star should produce extremes incompatible with sustained liquid water. Yet this planet defies each of these expectations. Observations indicate that the surface, atmosphere, and orbital conditions fall squarely within ranges that allow the persistence of liquid water and potentially stable chemical cycles. You consider the scale. The planet is enormous, many times Earth's radius. Yet gravity, though strong, does not prohibit layered atmospheric retention or stable surface liquids. Spectral analysis reveals chemical stratification. Thermal measurements show moderate ranges, and orbital data confirms a narrow but sustainable flux of stellar energy. By every metric you can measure, the planet satisfies the basic requirements for habitability. There is no evidence of catastrophic pressure, uninhabitable radiation, or unstable rotation that would preclude processes familiar to terrestrial life. Habitability is not determined by a single factor, but by the interaction of many. Atmospheric dynamics, tidal interactions, internal heat distribution, and rotation all contribute to the potential for a stable surface environment. On this planet, each of these elements appears to operate in concert. Partial tidal locking generates moderate internal heating without fracturing the crust. Rotation distributes energy evenly, preventing extreme day-night temperature gradients. Atmospheres remain layered despite extreme gravity. Thermal flux remains within bounds, conducive to liquid water. Every measurement implies that the planet exists in a narrow window of improbable equilibrium. The implications extend beyond the concept of Earth-like worlds. If planets of this size can maintain habitable conditions, the potential diversity of habitable worlds is vastly underestimated. Traditional models suggest that large planets are uninhabitable due to crushing gravity and extreme pressure. Yet observation shows that nature permits exceptions. Habitability may therefore not be a narrow niche confined to small terrestrial planets, but a broader domain that includes massive, extreme worlds that your intuition would initially reject. This observation also challenges assumptions about biological adaptation. Life on such a planet, if it exists, would encounter gravity, atmospheric pressure, and tidal regimes far beyond what terrestrial organisms experience. The chemical and physical environment would be extreme, yet coherent, structured rather than chaotic. Habitability is not a guarantee of life, but it is the precondition for complex processes to emerge, and the planet meets that precondition in every measurable way. You are confronted by the quiet paradox. The universe allows environments that are extreme by Earth standards, yet fully compatible with the persistence of familiar chemical and physical processes. Measurement, not speculation, confirms this. It is not that the planet might support life under unusual circumstances. It is that every observable parameter aligns with conditions that permit habitability. Gravity, atmosphere, rotation, heat, and orbital flux all converge to create a world that, by every metric you can measure, could sustain liquid water and, potentially, life. The planet forces a reconsideration of limits. Habitability is no longer strictly a function of size or stellar flux. It is the product of multiple interacting parameters, measured precisely, and capable of producing conditions you previously assumed improbable. Observation shows that extreme planets can exist within the habitable regime, expanding the scope of what is physically possible for life-sustaining environments. Ultimately, the implication is unsettling. A planet this large, with gravity and pressure so extreme, exists with surface conditions capable of sustaining familiar processes. Habitability, once thought to require modest planetary characteristics, emerges instead in improbable, finely tuned circumstances. The universe, in observation, permits worlds that challenge every preconception about where life could exist. The light you receive. You perceive starlight as predictable, a constant measure of energy input. Yet the variability of the star, measured over decades, produces fluctuations that are smoothed by the planet's atmosphere, creating a level of thermal stability that seems improbable given standard models. Stars are not perfectly constant. Observations of similar stars reveal subtle changes in luminosity over time, spots, flares, and cycles that modulate the energy emitted. On smaller planets, these variations can produce noticeable temperature swings, disrupting atmospheric circulation and surface conditions. On massive planets, with dense atmospheres and high gravity, such fluctuations are expected to amplify instability. Yet here, the incoming energy is absorbed, redistributed, and dampened in ways that maintain a surprisingly steady thermal environment. You examine the mechanism. Spectral data shows that the planet's atmosphere absorbs high-energy radiation efficiently, converting it into heat that is then redistributed through convection and radiation transport. Infrared measurements indicate that temperature differences between day and night are smaller than you would predict. Heat does not accumulate dangerously on the side facing the star, nor does it freeze on the night side. Light, as it arrives, is modulated passively, producing a planetary environment that is thermodynamically coherent despite the variability of the source. The smoothing effect is subtle but measurable. Fluctuations in stellar output occur on timescales ranging from hours to decades, yet atmospheric measurements show that their influence on surface temperature is muted. Convective currents transport energy vertically, while horizontal winds move heat across latitudes, maintaining a balance. Spectral absorption lines reveal that key greenhouse gases, including water vapor and carbon dioxide, respond to variations in a way that dampens extremes rather than amplifying them. The atmosphere behaves as a self-regulating system, not in defiance of physics, but in precise adherence to processes that are difficult to anticipate from first principles. You notice the implications for climate and habitability. On a planet with extreme mass, rapid rotation, and strong gravity, even minor variations in stellar flux could be catastrophic. Yet the system remains stable. Oceans, if present, would redistribute energy further through currents and mixing. Partial tidal locking contributes to moderation by shifting heating patterns gradually. The combination of orbital mechanics, stellar output, and atmospheric dynamics produces a finely tuned equilibrium that is improbable, yet directly observed. Even small perturbations, such as brief stellar flares or periodic changes in luminosity, do not appear to destabilize the planet. Measurements confirm that energy from the star is buffered by atmospheric processes, preventing extreme swings that would otherwise dominate climate and weather patterns. The planet is therefore capable of maintaining surface conditions suitable for persistent liquid water, despite being illuminated by a star that, by itself, would produce significant variability. You are confronted by a quiet paradox. The light you measure, assumed to be a simple constant, interacts with planetary systems in ways that produce unexpected stability. Stellar variability exists, yet its potential for disruption is mitigated. Physical laws are not broken, yet intuition fails. Observation confirms that extreme conditions, massive size, intense gravity, variable radiation, can coexist with an environment capable of maintaining thermal coherence. The planet demonstrates that the apparent constancy of starlight is a superficial simplification. In reality, energy input fluctuates continuously, yet atmospheric and orbital mechanisms redistribute it to maintain improbable stability. Every measurement, from photometry to infrared spectra, confirms this phenomenon. You realize that light, while familiar and seemingly simple, interacts with planetary environments in ways that defy expectation, producing conditions that are measured, real, and quietly extraordinary. Ultimately, the light you receive is not a simple measure of energy. It is filtered, modulated, and integrated across a system of forces, producing equilibrium where theory predicts chaos. Observation alone reveals the paradox. Starlight can vary, yet the planet remains unexpectedly stable, forcing a reconsideration of assumptions about the interaction between stars and the worlds they illuminate. Composition. Contradictions. Your mental model predicts dense interiors for massive planets. Spectral lines indicate an unusual mixture of silicates and volatiles, implying a composition more akin to smaller planets, yet spread over a much larger volume, a structural impossibility by classical standards. On Earth and other terrestrial planets, mass scales directly with density. A planet that is many times Earth's radius should have a proportionally denser interior to support the gravitational load. In standard planetary physics, silicates and volatiles cannot remain uncompressed at this scale. Pressures should produce exotic, high-density phases, and lighter elements should be driven to the surface or lost to space. Yet spectral analysis reveals familiar molecules distributed in ratios typical of smaller planets, implying a bulk composition that should not physically withstand the planet's gravity. The data comes from multiple observations. Transit spectroscopy provides insights into the atmospheric composition, while thermal emission and albedo measurements constrain surface and near-surface materials. Models that incorporate the measured mass and radius predict densities inconsistent with these compositions. The planet's interior must somehow maintain a distribution of lighter silicates and volatiles over a volume that classical physics suggests should collapse. Each line in the spectrum confirms that the material is present, stable, and behaving chemically as expected, even under extraordinary conditions. You examine the mechanics. Gravity should compress the lower layers, increasing pressure and temperature until silicates transition to higher density polymorphs. Water and volatiles should either dissociate, migrate upward, or be trapped in high-pressure ices. Instead, the observations indicate a planet in which silicates, water, and lighter compounds coexist at pressures far beyond those found on Earth, without undergoing expected structural transformations. This implies an internal equilibrium that is both improbable and measurable. Consider the implications for thermal and mechanical behavior. A massive planet with a light, familiar composition should deform, convect violently, or produce extreme volcanism. Yet the planet exhibits controlled internal heat distribution. partial tidal heating, rotation, and convective processes appear to operate in a way that preserves the structural integrity of the crust and mantle, allowing the lighter materials to persist in layers that are neither homogenized nor crushed. The planet defies the expectation that extreme mass inevitably leads to dense, exotic interiors. The paradox extends to the relationship between interior and atmosphere. Volatiles observed in the atmosphere, water vapor, carbon dioxide, trace methane, correspond to the unusual interior composition, outgassing processes that are normally accelerated under high pressure appear moderated. The atmosphere retains these compounds in ratios similar to smaller planets, even though the interior should have undergone chemical fractionation under immense gravitational stress. Spectroscopy confirms that these compounds exist in stable equilibrium, further contradicting conventional models. You are confronted by a quiet contradiction. Every measurement suggests a planet larger and more massive than theory predicts, yet composed of familiar elements arranged in familiar ratios. The classical expectation of crushing densities and exotic phases is not realized. Instead, observation confirms that the universe allows a structural regime where massive planets can maintain interiors resembling smaller worlds. It is a paradox derived entirely from measured reality, not speculation. Even minor variations in pressure, temperature, or rotational stress do not disrupt the observed compositions. The planet remains stable, its internal chemistry coherent, its viscosity, silicates, and volatiles persistent. The data leave no room for error or misinterpretation. The contradiction is imposed by measurement, verified across multiple observational techniques, and yet irreconcilable with intuition based on classical planetary physics. Ultimately, the composition contradictions illustrate a fundamental tension between expectation and observation. The planet is massive, yet internally familiar. Gravity, pressure, and structural mechanics suggest collapse, yet reality presents persistence. Silicates and volatiles endure where they should not, forming a stable system that defies classical structural limits. The planet exists as a measurable anomaly, a quiet reminder that even basic assumptions about planetary interiors can fail in the presence of extreme yet observable conditions. Surface pressure and water. Water is compressible. Pressure should prevent oceans from existing at high gravity. Yet spectroscopic absorption and transit timing variations suggest the presence of surface or near-surface liquid reservoirs, implying an atmospheric and hydrological system in tension with the planet's size. On Earth, the properties of water are well understood. Under extreme pressure, it transitions into high-density ice phases or becomes supercritical, unable to exist as a liquid. On a planet with gravity several times that of Earth, atmospheric pressure at the surface should compress any bodies of water to the point of phase transition. Oceans, lakes, or even shallow pools should be unstable. Yet observations indicate that water exists in conditions consistent with familiar liquid phases, forming layers that absorb and reflect starlight, producing absorption features in the planet's spectrum that can be distinguished from atmospheric moisture. The implications are immediate. Liquid water is fundamental to chemical processes associated with life as we understand it. Its persistence under such pressure contradicts expectations drawn from standard planetary physics. Thermal models indicate that surface temperatures, atmospheric pressure, and tidal interactions should collectively push water into exotic high-pressure forms. Instead, infrared and visible spectra suggest temperatures compatible with liquid water, while transit timing variations confirm the presence of an atmosphere capable of maintaining surface pressure within this narrow window. You examine the mechanisms that could allow this to occur. The atmosphere, dense and stratified, buffers pressure in ways that distribute force evenly across the surface. Partial tidal heating introduces internal energy that prevents complete freezing while avoiding runaway boiling. Convection and wind patterns redistribute heat, maintaining thermal uniformity. The result is a hydrological system capable of sustaining liquid water in spite of gravity that should, in theory, preclude it. Each process is observable, measurable, and internally consistent, yet collectively defies expectation. The paradox extends to surface stability. Even minor fluctuations in stellar flux or orbital eccentricity should cause water to transition rapidly between phases. Yet the planet exhibits moderation. Thermal inertia from the atmosphere, the stabilizing effect of rotation, and partial tidal heating combine to prevent extreme swings. Water persists in liquid form without evaporating into the upper atmosphere or being forced into high-pressure ice. The planet maintains a coherent hydrological cycle, implying rivers, oceans, or shallow reservoirs could exist in a system under extreme mass and gravity. You begin to see the broader implications. Surface water is more than a chemical curiosity. It is a measurable indicator of equilibrium in an extreme planetary system. Gravity, pressure, atmospheric density, temperature, and tidal energy are all extreme compared with terrestrial norms. Yet observation confirms the coexistence of liquid water. It is a quiet, precise contradiction. The planet should be hostile to hydrological stability, yet it is observable and consistent with predictions based on measurement. Even minor perturbations, stellar flares, atmospheric turbulence, or shifts in orbital eccentricity do not appear to destabilize the water. The planet's internal and surface systems operate in a delicate balance that preserves liquid reservoirs. The measurements are unambiguous. Water exists under conditions that classical physics would suggest are impossible, maintained through a combination of atmospheric buffering, thermal distribution, and precise orbital mechanics. Ultimately, the presence of surface or near-surface water underscores the quiet paradox of this planet. Observation confirms what intuition cannot easily accept. Extreme gravity and pressure do not preclude the existence of liquid water. Spectroscopy, transit timing, and thermal modeling all indicate the persistence of a system that challenges assumptions about planetary hydrology. The planet exists in a regime where water, under immense pressures, remains familiar in behavior and properties, quietly defying the constraints you once assumed to be universal. Magnetic fields and shielding. You understand magnetic fields as generated by rotation and internal convection. The planet's inferred field strength appears both strong and unusually coherent, capable of protecting the atmosphere from stellar winds, a contradiction given the slow, dense interior predicted for such a massive world. Magnetic fields arise from the motion of conductive materials within a planet's interior, typically molten iron or other metals, combined with rotation. In massive planets, however, extreme gravity and high internal pressures should suppress convective motion, slowing or even stalling the dynamo process. The expectation is clear. A slow, dense interior should produce a weak, disorganized magnetic field, unable to shield the atmosphere from high-energy particles emitted by the star. Yet observations, inferred from auroral emissions and interactions with stellar wind, indicate a field both strong and coherent. The implications are immediate. A coherent magnetic field serves as a protective barrier, preventing atmospheric erosion and deflection of charged particles. Without such shielding, the planet's atmosphere would gradually strip away under the influence of the star, reducing pressure and destabilizing the hydrological cycle. Measurements of transit spectra indicate atmospheric stability, suggesting that the magnetic field functions effectively, despite expectations based on mass and internal structure. You examine the mechanisms that could support this. Rotation contributes to the dynamo, though the planet spins at a moderate rate rather than an extreme velocity. Internal convection, despite high pressure, appears sufficient to generate organized currents. It is not turbulence alone, nor rotation alone, but the precise interaction of both factors that produces a field coherent over planetary scales. This dynamo exists in a regime where classical models predict collapse of convective motion, yet observation confirms persistent, measurable magnetism. The field also shapes interactions with the star. Incoming charged particles are diverted along magnetic lines, producing auroral emissions and protecting lower atmospheric layers. Radiation that might otherwise break molecular bonds or heat the upper atmosphere is deflected or absorbed. The planet maintains an environment in which atmospheric gases remain chemically stratified and thermally moderated. In other words, the magnetic field, derived from physical processes that should be weak or disordered, sustains the observable conditions that allow liquid water and atmospheric layering to persist. You notice a deeper paradox. The planet's size and mass suggest internal pressures that would inhibit fluid motion. Yet the dynamo continues. It is neither chaotic nor intermittent. The field is steady, measurable, and aligned across planetary scales. Minor variations in rotation or internal temperature do not disrupt its coherence. Observation, not speculation, confirms that magnetic shielding exists and functions, even under conditions where it should be improbable. Even more subtly, the field has indirect effects on climate and surface stability. By protecting the atmosphere from erosion and high-energy particle influx, it allows heat, gases, and water to remain in equilibrium. Without it, even moderate stellar flares could strip the atmosphere, destabilizing the delicate thermal and chemical balances previously observed. The magnetic field is therefore not merely a physical property. It is an integral component of the planet's habitable system, quietly sustaining conditions that seem impossible given mass and internal density. Ultimately, magnetic fields on this planet illustrate a tension between expectation and observation. You anticipate weakness and disorganization, yet find strength and coherence. Forces that should fail under extreme mass instead operate effectively, producing observable consequences that preserve atmospheric integrity and surface conditions. Every auroral signature, every deflection of stellar wind, confirms that the planet maintains a protective shield under circumstances that theory suggests should be hostile to it. Observation forces you to recognize a subtle but profound fact. Extreme physical parameters do not preclude complex planetary systems from functioning in coherent, life-permitting ways. The magnetic field exists as a measured, real, and precisely balanced phenomenon. It is another quiet defiance of expectation, another demonstration that the universe allows improbable stability in the presence of extreme forces. Geological activity. Massive planets should cool slowly, locking interiors and freezing surface dynamics. Yet evidence of volcanism and tectonic activity appears in indirect measurements implying persistent internal heat generation that defies conventional geophysical models. On smaller planets, internal heat comes from a combination of residual formation energy, radioactive decay, and tidal interactions. Over geological time, heat escapes through conduction and convection, gradually cooling the interior. On massive planets, the expectation is that the enormous gravitational compression would increase the rate of heat transfer. Yet the interior should also be stabilized by immense pressure, producing a rigid, slow-moving mantle incapable of significant convection. Any tectonic activity should have ceased long ago, leaving the surface largely static. Observations, however, suggest otherwise. Thermal emission data, combined with variations in transit timing and stellar absorption lines, indicate hotspots consistent with volcanism and mantle upwelling. Small fluctuations in emitted infrared radiation reveal localized heating events, and minute changes in ISO, the planet's gravitational signature, hint at mass redistribution within the crust and mantle. These are subtle signals, but they are measurable and repeatable. They suggest active geology, not merely residual thermal anomalies. The interior is mobile, and the surface responds accordingly. You consider the sources of this heat. Partial tidal locking with the star introduces cyclical flexing, producing friction within the mantle. The scale of this effect is magnified by the planet's size and mass, yet it is regulated in a way that prevents catastrophic deformation. Convection within the mantle transports energy efficiently, while rotation distributes stress across the interior. The result is a slow but continuous geological engine capable of generating tectonic and volcanic activity over observable timescales. It is a dynamic system operating under extreme constraints, producing measurable outcomes that should, by classical understanding, be impossible. The consequences extend to surface composition and atmospheric chemistry. Outgassing from tectonic and volcanic activity replenishes the atmosphere with water vapor, carbon dioxide, and trace gases. These compounds, in turn, contribute to thermal regulation and chemical stratification. The coupling between interior and atmosphere is subtle yet critical. Observation confirms that active geology sustains atmospheric processes, which themselves moderate surface conditions and contribute to the persistence of liquid water. The planet is not merely geologically active. It is geologically integrated into a system that maintains equilibrium under extreme conditions. Even minor perturbations, such as stellar flares or variations in orbital eccentricity, do not appear to disrupt this activity. Heat generation is steady, balanced, and measurable across multiple observation methods, convection patterns persist, volcanic hotspots remain localized, and tectonic motions continue without catastrophic instability. The planet's interior operates in a regime that is extreme, yet coherent. Classical models would predict a frozen mantle, yet observation demonstrates that mobility is preserved. You are confronted by a quiet paradox: extreme mass, high gravity, and internal pressures that should inhibit convection instead coexist with persistent, measurable geological activity. The planet demonstrates that energy dissipation, tidal interaction, and mantle convection can combine to produce internal motion under conditions that are both extreme and stable. Every thermal signature, every mass redistribution measurement confirms the presence of dynamic geology, a phenomenon that classical geophysics would deem improbable. Ultimately, geological activity on this planet reinforces a pattern seen in every other measurement. The universe allows extreme systems to operate in stable, life-permitting ways. The interior is neither frozen nor chaotic. It is a functioning engine, observable, measurable, and consistent. Tectonics and volcanism continue where theory suggests they should not, quietly sustaining the planetary systems necessary for habitability. Geological activity exists as another reminder that the universe permits equilibrium in conditions that intuition would reject. Impacts of scale. You assume scale magnifies instability. Yet this planet's orbital and rotational measurements indicate a system stable over millions of years. Scale, rather than producing chaos, appears to have produced a kind of enduring equilibrium. On larger planets, every physical parameter, mass, gravity, atmospheric density, internal pressure, exerts an amplified influence. Minor perturbations that would be negligible on Earth-sized planets become dominant forces. Rotation, tidal interactions, and thermal flux should create instabilities that cascade through the atmosphere, interior, and orbital mechanics. Yet here, observation shows a system that is coherent, predictable, and remarkably resilient. Measurements of orbital period, transit timing, and stellar wobble confirm long-term stability, with variations limited to imperceptible fractions of a percent. You examine the mechanisms of this stability. Large mass increases gravitational binding, which constrains deformation and limits the amplitude of oscillations in the crust and atmosphere. Rotation distributes energy efficiently, while partial tidal locking moderates internal heat and stabilizes day-night temperature differences. The atmosphere, dense and stratified, buffers radiation and smooths thermal fluctuations. Every measurable property interacts with every other in a network of feedbacks that preserves equilibrium rather than amplifying chaos. Scale, in this context, does not produce disorder. It enables precise self-regulation. Consider the orbital configuration. A planet of this size should be highly sensitive to perturbations from nearby planets or the star itself. Yet long-term observations indicate a stable orbit with eccentricity, inclination, and semi-major axis remaining effectively constant over millions of years. Stellar gravitational interactions, which would normally excite oscillations or secular drift, are absorbed and moderated by the planet's mass and rotation. Energy that might destabilize smaller systems is here redistributed, diffused across a volume and mass large enough to prevent catastrophic effects. The paradox extends to internal dynamics. The enormous interior should amplify convective irregularities, producing unpredictable mantle flow or erratic volcanic activity. Yet thermal and geological measurements indicate patterns that are consistent and repeatable. Partial tidal heating introduces energy at rates sufficient to sustain internal motion, yet not enough to disrupt equilibrium. Convection, rotation, and heat transport appear coupled in ways that stabilize the interior, producing measurable geological activity that persists without producing catastrophic deformation. Scale, which should magnify instability, instead stabilizes the system across multiple domains. You notice the implications for atmospheric behavior. High gravity and dense atmospheric composition could produce extreme winds or collapse layers under minor perturbations. Yet circulation patterns, measured through spectral absorption and thermal emission, remain regular and coherent. Weather systems, if present, appear moderated by planetary rotation, thermal inertia, and the coupling between internal heat and surface temperature. The atmosphere behaves as a system tuned to the planet's scale, absorbing energy that might otherwise destabilize it. Even minor external events, such as stellar flares or orbital resonance with other planets, do not disrupt the observed stability. Scale allows the planet to absorb and dissipate energy across its mass and volume, producing resilience rather than vulnerability. Observation confirms that extreme size does not automatically generate chaos. It can produce a coherent system in which forces balance in precise and measurable ways. Ultimately, the impacts of scale are quietly paradoxical. The planet's enormous mass and size, rather than threatening instability, create conditions for long-term equilibrium. Every measurement, from orbital dynamics to internal motion, from atmospheric distribution to thermal flux, demonstrates a system stable where theory would predict disruption. Observation, not speculation, confirms that scale can produce order, enabling a planet to sustain conditions that should be impossible for a body of this magnitude. The universe allows extremes to operate coherently, revealing a subtle balance that is measured, real, and quietly unsettling. Observing through light. Years. All information comes through photons that have traveled immense distances. You trust this data, yet the light itself carries distortions from intervening space. Even with this uncertainty, the physical parameters of this world remain consistent, suggesting that improbability is not observational error. When you observe distant planets, every measurement is filtered through the vastness of space. Photons travel for years, decades, or even centuries, interacting subtly with interstellar dust, magnetic fields, and gravitational wells. Each interaction introduces potential distortion. Absorption. Lines shift, fluxes fluctuate, and spectra are smeared. Despite this, multiple independent observations converge on the same conclusions. The planet's size, mass, atmospheric composition, rotation, and orbit are consistent across instruments, time periods, and observational platforms. The improbabilities you see are real. You consider the implications of light travel time. What you measure is an echo of the past, a record frozen in photons. Variability in the star, atmospheric turbulence, and internal dynamics all occurred long before the light reached your detectors. Yet the parameters derived from this ancient information are precise. Orbital periods, rotational speed, and atmospheric layering remain coherent when extrapolated forward, indicating that the system is not only measurable, but stable over timescales far exceeding human observation. The improbability of this equilibrium is intrinsic to the planet itself, not a byproduct of observational uncertainty. Intervening space imposes additional challenges. Interstellar gas and dust absorb specific wavelengths. Gravitational lensing bends photon paths, and cosmic radiation introduces noise into sensors. Yet repeated measurements across spectral bands produce consistent results. Transit photometry, radial velocity, infrared emission, and spectroscopy all align, each confirming the same physical parameters. The planetary radius inferred from transits corresponds to the density suggested by mass estimates. Atmospheric composition derived from absorption lines aligns with thermal modeling. These confirmations occur despite the distortions imposed by vast distances. The stability implied by these measurements is quietly unsettling. You are effectively inferring a complex, dynamic system across light years. Yet the system behaves in ways that are improbable yet real. Partial tidal locking, coherent magnetic fields, layered atmosphere, persistent hydrology, and geological activity all manifest consistently. The improbabilities are not artifacts of measurement. They are properties of the planet itself. Every photon carries evidence of a system that exists in equilibrium under conditions that should, by classical expectations, be inhospitable to stability. You also notice the limits of certainty. Light carries time with it. The parameters you observe are snapshots from a past era. Any variation that occurred after emission is invisible. Yet, by cross-referencing independent observation epochs, you detect no anomalies. The planet's equilibrium persists. Observational error, instrumental bias, or cosmic interference cannot account for the coherence of these measurements. The universe has produced a system that operates under extreme constraints, measurable despite the enormous distance separating observer and object. Even minor discrepancies are informative. Slight variations in flux or spectral line intensity are expected and observed, but they fall within predictable ranges that are consistent with atmospheric dynamics and stellar variability. There is no evidence that the improbabilities you see, the delicate balance of rotation, gravity, atmospheric pressure, and tidal interactions, are illusions. Each measurement reinforces the conclusion. Extreme stability exists in a system that should, by every expectation, be unstable. Ultimately, observing through light years underscores a quiet paradox: distance and distortion, which could easily undermine confidence in measurement, instead reveal the persistence of improbable equilibrium. The planet's properties are consistent, stable, and coherent, transmitted across vast spatial and temporal gaps by streams of photons. The improbable balance is not imagined nor measured imperfectly. It is real, and it is observable. In this way, the universe confirms, through light alone, the existence of stability under conditions that should be impossible, leaving you to confront the disquieting precision of the cosmos. Orbital resonances. Planets in close proximity tend to fall into resonant orbits. This planet exhibits resonances that are mathematically stable yet rare, implying a dynamical history that is both specific and precise, a narrative embedded in orbital mechanics itself. Resonance occurs when orbital periods of two bodies form a ratio of integers, producing predictable gravitational interactions. In most planetary systems, resonances are either transient or unstable, disrupted by perturbations from neighboring planets, tidal forces, or stellar evolution. Yet here, careful measurements of transit timing variations, orbital inclination, and stellar wobble indicate a resonance that persists across millions of years. The ratios are precise, maintained over timescales long enough to influence tidal heating, rotation, and even internal convection. You consider the improbability. Resonances of this type are rare because they require both precise initial conditions and minimal external disturbance over geological time. Slight changes in eccentricity, orbital inclination, or nearby planetary masses typically destabilize these ratios, leading to chaotic orbits, collisions, or ejections. Yet this planet's resonance is coherent, suggesting that its formation and subsequent evolution were fine-tuned in a manner that produces both stability and measurable physical consequences. The resonance also interacts with other systems. Partial tidal locking, internal heating, and rotational dynamics are modulated by the orbital ratios. Tidal energy is delivered at intervals that produce predictable flexing without causing catastrophic stress. The planet's rotation remains stable, contributing to the regulation of atmospheric circulation. Geological activity, driven in part by tidal heating, aligns with the timing of orbital forcing. Each process, while extreme, is synchronized through resonance, producing a coherence that is unlikely yet observable. Observationally, the resonance manifests in subtle ways. Transit timing variations reveal minute deviations consistent with gravitational interactions between the planet and its neighbors. Radial velocity measurements of the star show periodic shifts that match predicted resonance patterns. Even minor deviations are absorbed by the system without cascading into instability. The orbital arrangement is therefore not merely a curiosity, it is a functional component of the planet's overall stability. You notice a quiet implication. The resonance is evidence of history encoded in mechanics. The system did not arrive at this configuration by chance alone. Its current state reflects a sequence of events: formation, migration, interaction with siblings, and tidal evolution, each constrained by physical law and initial conditions. The resonance preserves these histories in the structure of the orbit, measurable from light years away, yet unfolding over timescales far beyond human perception. The rarity of such resonance raises another paradox. Classical models of planet formation and migration predict that extreme mass planets in dense systems should disrupt resonances, producing chaotic orbital evolution. Yet this planet maintains its ratio precisely. The improbability is compounded by the fact that resonances influence every dynamic process on the planet: tidal heating, rotation, geological activity, atmospheric circulation. Each measurable property is tied, subtly but inextricably, to the resonance itself. Even perturbations from the star or minor moons do not destabilize the orbital ratio. The system absorbs energy, redistributes momentum, and preserves the pattern across geological timescales. Observation confirms that the resonance is functional, not incidental. It coordinates internal and external processes, producing a planetary environment in which extreme forces coexist with precise equilibrium. Ultimately, orbital resonances reveal the quiet architecture underlying the planet's improbabilities. The system is mathematically precise, dynamically stable, and intimately connected to tidal, rotational, and geological phenomena. Observation, rather than speculation, shows that resonance is not an anomaly. It is a central organizing principle that permits a massive, extreme planet to exist in coherence. Scale, history, and physics converge, embedding improbability into the very mechanics of motion, leaving you to confront a universe in which stability can emerge under conditions that seem unlikely at every level. The limits of models. Models predict impossible conditions for habitability at this scale. Observations show that the planet exists exactly where models say it cannot. The tension between theory and measurement is not trivial. It is fundamental. Planetary science relies on a series of assumptions: that gravity scales predictably with mass, that atmospheres cannot maintain structure under extreme pressure, that internal dynamics slow as mass increases, and that orbital and tidal interactions destabilize large systems. These assumptions form the basis of models used to predict planetary properties, habitability, and internal processes. Yet here, each assumption is challenged by direct observation. The planet exists with stable gravity, layered atmospheres, persistent internal heat, liquid surface water, and coherent orbital dynamics, all simultaneously measurable and internally consistent. You recognize the implications. Models are not merely inaccurate, they are incomplete. They fail to account for the emergent coherence of multiple interacting parameters in extreme conditions. Gravity, pressure, atmospheric layering, tidal heating, rotation, and orbital resonance combine in ways that are predictable in hindsight, but cannot be derived from linear extrapolation. The planet operates in a regime outside the predictive envelope of conventional physics applied to terrestrial planets, exposing the limits of theoretical frameworks. Observational data reinforces this contradiction. Transit photometry, radial velocity, infrared emission, and spectroscopy all independently confirm the planet's properties. Internal heat, magnetic fields, surface water, and chemical cycles exist exactly as predicted by measurement, but exactly contrary to expectation based on models. The improbabilities are not artifacts of error, bias, or insufficient sampling. They are intrinsic to the system. Every measurement emphasizes that theory cannot fully anticipate the behavior of extreme worlds. You examine the mechanisms that might reconcile observation with expectation. Some processes, partial tidal locking, orbital resonance, atmospheric stratification, magnetic shielding, interact to produce emergent stability. Individually, each might seem improbable. Collectively, they create a system that is coherent, self-regulating, and habitable under conditions where models predict instability. The models, by their very construction, fail to capture the interplay of these factors across extreme scales, revealing that theoretical extrapolation can mislead when applied beyond the domain of Earth-like planets. The paradox extends to habitability itself. Models define habitable zones based on temperature, stellar flux, and size constraints derived from known planets. Yet, this world exists comfortably within the habitable range, despite exceeding size and mass limits that theory predicts as uninhabitable. Surface water, atmospheric composition, and thermal stability all persist, contradicting model expectations. The discrepancy is not subtle. It is observable, measurable, and persistent. Habitability emerges where classical reasoning would rule it out entirely. Even the simplest assumptions are challenged. Density scaling, thermal equilibrium, and gravitational compression, considered nearly immutable, are defied in measurable ways. The planet maintains a low average density for its size, a layered atmosphere under high gravity, and moderate surface temperatures. These properties exist in a mutually consistent system, yet they lie beyond the predictive power of conventional models. Observation forces a reconsideration of the rules themselves. Ultimately, the limits of models reveal the tension between abstraction and reality. Models are simplified representations, necessary for understanding, yet they cannot fully anticipate the behavior of systems operating at extremes. The planet exists not as a failure of observation, but as a failure of expectation, an existence that is mathematically improbable, physically extreme, yet empirically undeniable. Measurement insists on the reality of a system that theory alone cannot predict, leaving you to confront the quiet but profound truth. The universe allows conditions that extend beyond the limits of the models you rely upon, and the evidence is visible, consistent, and precise. Comparative planetology. You compare worlds to understand them. Every massive planet known to us exhibits extremes incompatible with life. Yet this planet, by contrast, mirrors his Earth-like qualities, despite its enormous mass. A counterexample in the dataset, forcing reconsideration of planetary classification. In conventional planetary studies, mass is a defining predictor of properties. Gas giants possess thick hydrogen-helium envelopes, extreme pressures, and volatile interiors, while smaller terrestrial planets retain solid surfaces, moderate gravity, and atmospheres capable of sustaining familiar chemistry. Exceeding a certain size typically precludes Earth-like conditions. Dense interiors, strong gravity, and destabilized atmospheres dominate, leaving little room for stable liquid water or stratified gases. Yet here, a planet with mass several times that of Earth maintains conditions that are measurable, consistent, and superficially familiar. Observationally, the contrast is stark. Measurements of radius, density, surface gravity, atmospheric composition, and thermal flux reveal a system that does not fit neatly into established categories. Spectroscopy indicates water vapor and carbon dioxide in ratios similar to smaller planets. Thermal infrared data shows moderate surface temperatures, and transit timing reveals stable orbital mechanics. The planet behaves like a terrestrial world in almost every relevant sense, yet exists at a scale traditionally associated with inhospitable extremes. You examine the dataset. Other massive planets exhibit high-pressure interiors, thick envelopes of hydrogen and helium, or rapid rotational periods that produce chaotic weather and extreme temperature gradients. Internal convection is either suppressed or dominated by exotic high-pressure phases. The atmosphere, if present, is homogenized, unlayered, and chemically simple. By comparison, this planet's atmosphere is stratified, layered, and chemically diverse. Water remains liquid. Heat is redistributed efficiently. Its mass should magnify every instability observed elsewhere, yet instead produces coherence. The implications for planetary classification are subtle but profound. If mass alone does not predict atmospheric behavior, hydrological cycles, or geological activity, then current taxonomies may obscure the true diversity of planetary systems. Planets, once considered too massive for habitability, now require closer examination. Observational evidence forces you to reconsider the thresholds of what is Earth-like or habitable, expanding the parameter space in which life-supporting conditions could plausibly exist. You also notice the interactions between extreme mass and planetary systems. Large planets tend to stabilize moons and rings, affect orbital resonances, and influence tidal forces. In typical massive planets, these forces produce chaos in smaller neighboring worlds. Here, orbital stability is preserved, resonances are precise, and tidal heating is sufficient to drive geological activity without catastrophic deformation. The extremes of mass amplify stability rather than undermine it, a pattern absent in smaller comparative datasets. Even the planet's chemical cycles are inconsistent with analogs. Volcanic outgassing, atmospheric stratification, and water cycling operate as if mass were secondary. Observations indicate that extreme size neither homogenizes chemical layers nor inhibits geological renewal. Instead, the system functions in ways analogous to terrestrial planets, producing patterns of energy and material flow that are familiar, yet occurring under conditions that models would predict as impossible. Ultimately, comparative planetology reveals a paradox. The planet exists at a scale where extremity should dominate, yet it maintains coherence and Earth-like qualities. Observation forces you to recognize that the rules derived from smaller planets are not universal. Extremes can produce stability, and Israel does not preclude the persistence of familiar planetary systems. In comparing worlds, you see not merely an anomaly, but a measurable demonstration that the universe permits configurations that defy expectation. The counterexample is concrete, observed, and precise, a quiet challenge to the frameworks through which you interpret planetary systems. The role of uncertainty. Every measurement carries error. Here, even accounting for uncertainty, the conclusion is unchanged. A massive, potentially habitable planet exists. The contradiction is not an artifact. It is the observable outcome. In any scientific observation, every parameter, mass, radius, atmospheric composition, orbital period, or thermal emission, comes with a margin of error. Instruments have limitations. Light is distorted by interstellar material, and data processing introduces statistical uncertainty. Yet, even when these factors are considered, the planet's extreme properties persist. Mass estimates remain high, radius measurements confirm low density, atmospheric signals indicate stratification and water vapor, and orbital analyses reveal long-term stability. Uncertainty, rather than resolving the paradox, only reinforces its persistence. You consider the robustness of this conclusion. Observations from multiple instruments across different spectral ranges converge on consistent values. Transit photometry defines radius within narrow limits. Radial velocity measurements constrain mass, independent of transit data. Infrared spectroscopy identifies molecular absorption features repeatedly across different epochs. Even accounting for the error margins of each method, the probability that all measurements could produce this coherent but improbable picture by coincidence is vanishingly small. The planet's existence is real, measurable, and resilient to observational uncertainty. The paradox extends to the planetary system as a whole. Orbital resonance, partial tidal locking, rotational period, and internal heat distribution are all derived from observations with finite precision. Errors in these measurements could, in theory, make the system appear less extreme or more unstable. Yet the observed parameters remain consistent with the existence of a planet capable of sustaining familiar physical processes despite its mass. Uncertainty does not blur the contradiction. It defines the boundaries within which the improbability persists. You begin to see the philosophical implications. Scientific models often assume that improbable measurements will resolve into ordinary explanations once uncertainties are accounted for. Here, that assumption fails. The planet is extreme, yet stable. Every adjustment for measurement error preserves the anomaly. Statistical noise does not explain it. The paradox is embedded in reality itself. Measurement affirms the existence of conditions that defy classical planetary expectations. Even the smallest observational ambiguities reinforce the conclusion. Minor variations in spectral lines or transit timing do not undermine the presence of water vapor, layered atmospheres, or coherent orbital dynamics. Each independent dataset produces a result compatible with the previous one, and together they define a planet whose properties are extreme, yet internally consistent. The interplay of uncertainty and observation strengthens the conclusion. Improbable stability is not an artifact of instrumentation or method. The role of uncertainty is therefore subtle but critical. It frames the limits of your confidence. Yet even at the extremes of error, the system persists. Every correction, every statistical adjustment confirms that a massive, potentially habitable planet exists where theory predicts collapse or inhospitability. The universe permits configurations that remain coherent and measurable, even under conditions that models would dismiss as impossible. Ultimately, uncertainty emphasizes the quiet dissonance between expectation and observation. You cannot dismiss the contradiction by invoking error, nor can you rationalize it away as observational bias. Measurement, refined and repeated, persists in revealing a system that is extreme yet balanced, improbable yet real. The planet exists as a concrete, measurable paradox, resilient to uncertainty. And it forces recognition that the cosmos permits stability and habitability under conditions far beyond those imagined in conventional theory. Implications for life. If life could exist on a planet of this size, it suggests that biological possibility is broader than assumed. Yet the very mechanisms that would allow life, stable atmosphere, water, magnetic protection, arise under conditions our models deem incompatible. On Earth, habitability is constrained by gravity, atmospheric retention, surface pressure, temperature, and energy input from the star. Each parameter falls within a narrow range that permits stable chemistry, liquid water, and cycles of energy and material essential for biological processes. On this massive planet, those same parameters appear extreme. Surface gravity is high, internal pressure enormous, and the atmosphere dense. Yet measurements indicate that the fundamental conditions for life persist. Water remains liquid, gases remain stratified, magnetic shielding deflects harmful radiation, and thermal flux remains moderated. The combination is rare and unexpected. You consider the scale of the implications. Life, as a set of chemical and physical processes, depends on environmental stability. On planets smaller than Earth, perturbations are damped more easily. On planets larger than Earth, instabilities should overwhelm chemical networks. Yet here, the system demonstrates coherence across multiple domains. Orbital stability, tidal heating, internal convection, and atmospheric regulation combine to produce a steady state. If chemical processes are sustained, they do so in a context that challenges existing assumptions about environmental thresholds. Biology, in principle, could exist in regimes previously deemed inaccessible. Observations of the planet reinforce the paradox. Spectroscopy reveals water vapor, carbon dioxide, and other trace molecules in ratios consistent with familiar geochemical cycles. Thermal measurements show day-night and seasonal variability within ranges compatible with energy-driven chemical reactions. Magnetic shielding, inferred from auroral emissions and interactions with the stellar wind, indicates that ionizing radiation at the surface is likely moderated, preserving molecular integrity. All of these factors coalesce into a planetary environment that is, from a physicochemical standpoint, compatible with the persistence of life. Like chemistry. Yet the very presence of these conditions under extreme mass is unsettling. Gravity should suppress convection. Tidal forces should destabilize rotation. Pressure should collapse liquid reservoirs, and atmospheric density should homogenize chemical layers. Each of these expectations is violated. Life-supporting processes emerge in a system that classical models suggest should be inhospitable. The mechanisms that enable habitability are not hypothetical. They are observable, measurable, and internally consistent, yet arise in a context that defies intuition. You recognize a deeper implication. If one planet of extreme size supports conditions suitable for life, then the domain of potential habitability expands. Exoplanet surveys often focus on Earth-sized or slightly larger planets, guided by assumptions derived from terrestrial experience. This planet demonstrates that mass, size, and gravity are not absolute barriers. Stability and life-permitting chemistry can arise through a balance of interacting forces, emergent properties, and finely tuned feedbacks observable across light years. Even minor deviations in any parameter, rotation, atmospheric density, tidal forcing, could destabilize conditions. Yet all measurements indicate persistent equilibrium. Stability is not a fluke. It is embedded in the structure and dynamics of the planet. The possibility of life, therefore, is not merely a theoretical extrapolation. It is a logical consequence of a system that is extreme yet coherent. Ultimately, the implications for life are quietly disconcerting. The universe may allow biology in regimes far broader than Earth-based intuition would suggest. The conditions that support life emerge naturally from systems that, by conventional expectation, should preclude it. Observation confirms not only that extreme planets can exist coherently, but also that such worlds may harbor environments suitable for the complex processes we associate with living systems. The paradox is real, measurable, and unresolved. Habitability exists where theory predicts impossibility, forcing a reconsideration of the limits of biological possibility. Observational confirmation, multiple instruments, independent surveys, and years of tracking have converged on the same parameters. Redundancy removes doubt, leaving only the disquieting reality that observation consistently defies expectation. When you examine a distant world, every measurement carries the potential for error. Instrumental calibration, data reduction methods, and environmental interference all introduce uncertainty. Normally, repeated observations are expected to refine understanding, correcting anomalies, and converging on predictable outcomes. Here, however, the convergence is not toward expectation, but toward improbability. Mass, radius, rotation period, orbital stability, atmospheric composition, and thermal characteristics all remain consistent across independent methodologies. Every instrument, every survey, and every epoch confirms the existence of a planet that should, by conventional models, be uninhabitable. Transit photometry and radial velocity studies provide the first layer of confirmation. Transit depth and timing define radius and orbital period, while radial velocity measures stellar reflex motion, constraining mass. Each technique, sensitive to different systematic errors, yields results that align precisely. Discrepancies fall within statistical uncertainty, yet do not alter the conclusion. The planet is massive, yet low density. It is extreme, yet stable. Independent observation reinforces, rather than undermines, the apparent contradiction between expectation and reality. Spectroscopic surveys add another dimension. Measurements of atmospheric absorption lines indicate the presence of water vapor, carbon dioxide, and other trace compounds. Observations across multiple wavelengths, from near-infrared to mid-infrared, consistently detect these features. Different telescopes, using distinct methods of light dispersion and calibration, reproduce the same chemical signatures. The stratified atmosphere is confirmed, implying pressure and temperature distributions that models predict should be unstable. Redundancy removes the possibility that a single dataset or instrument error could produce this coherent signal. Long-term monitoring provides temporal consistency. Orbital resonance, rotation, tidal effects, and thermal emission are measured across decades. Minor fluctuations occur, as expected in any planetary system, yet the system remains coherent. Stability is not a short-lived coincidence. It is persistent, observable, and predictable within measurement precision. Observational confirmation, in this sense, reveals that the improbable behavior of the planet is not ephemeral. It is a measurable feature of reality. You recognize that the implications extend beyond this planet. Each independent confirmation emphasizes a universal principle. The universe allows systems to exist in regimes previously thought impossible. Where theory predicts collapse or instability, measurement demonstrates equilibrium. Where expectation predicts homogenization, observation shows stratification. Redundancy does not simplify the paradox. It amplifies it. Observation itself becomes a disquieting witness to the universe's tolerance for extremes. Even minor anomalies in the data are informative. Slight variations in flux, spectral line intensity, or transit timing fall within predicted ranges for atmospheric dynamics or orbital interactions. They do not compromise the overarching conclusion. Every confirmed property, size, mass, atmospheric composition, internal activity, contributes to a coherent, measurable system in which improbability is real and persistent. The planet exists, not as an anomaly that might be explained away, but as a feature reinforced by multiple lines of independent evidence. Ultimately, observational confirmation imposes an unavoidable recognition. It is no longer possible to dismiss the existence of this massive, potentially habitable planet as a fluke, an error, or a statistical artifact. Every layer of redundancy, every instrument, every epoch, every independent survey converges on the same conclusion. The measurements themselves, precise and consistent, force you to confront a reality in which the improbable is stable, the extreme is coherent, and expectation is repeatedly defied. Observation confirms that the universe allows the existence of worlds that challenge your assumptions, and it does so without hesitation, without ambiguity, and without resolution. The scale of perception. Your mind scales. Planetary sizes relative to Earth. This planet forces you to confront dimensions that strain intuition. Observation is precise, yet your cognitive map struggles, revealing the limits of perception itself. Humans naturally evaluate planetary mass, radius, and gravity through the lens of Earth-like experience. A world twice or 3 times the size of Earth can be imagined, roughly scaled in your mind. But beyond a certain magnitude, the familiar heuristics fail. Gravity becomes a pressure not just on objects, but on your sense of what surface means. Atmospheric layers seem impossibly thick. Oceans feel compressed under the sheer weight of the sky. And internal processes operate at scales that defy intuitive extrapolation. Observation quantifies these properties precisely, yet your mind is ill-equipped to internalize them. You notice the dissonance between measurement and intuition. Transit depth defines radius within a few percent. Radial velocity constrains mass. Spectroscopy reveals chemical composition. And thermal emission provides temperature estimates. Each value is reliable, consistent, and repeatable. Yet your cognitive framework strains to visualize the implications. How can water remain liquid under gravity twice or 3 times Earth's? How can the crust support mountains and oceans without collapsing? Each answer exists in calculation, but the mind struggles to translate number into intuition. Perception falters further when considering dynamic processes. Rotation, orbital resonance, tidal heating, and convection operate on scales far larger than Earth-based experience. The energy flows and material cycling that sustain equilibrium occur across volumes and masses that cannot be fully grasped through mental models designed for smaller systems. Yet observation demonstrates coherence. The planet's systems function precisely as measurement predicts. Stability emerges where instinct suggests collapse should dominate. Your difficulty is compounded by time scales. Geological processes, atmospheric circulation, and orbital evolution unfold over millions of years. You perceive only snapshots, mediated through light years of travel. Light encodes these vast scales into observable parameters, yet your mind compresses them into familiar temporal frames, producing cognitive tension. The planet exists fully outside the realm of immediate human perception, yet its properties are measurable, tangible in data, and real. Even chemical and physical extremes challenge perception. Atmospheric pressure, surface gravity, and internal convection operate at magnitudes that strain earthbound reasoning. Water exists as a liquid under pressures that seem intolerable. Magnetic fields, partially generated through rotational dynamics and internal convection, maintain protective shielding over a mass that should suppress coherent currents. Observation confirms these processes occur reliably, yet the mind cannot fully integrate their scale. You realize that the planet's improbabilities are inseparable from their magnitude. It is not merely the physical properties that defy expectation. It is the very act of perceiving them. Human intuition, evolved to navigate terrestrial scales, fails when confronted with planetary extremes. Measurement is precise, reproducible, and consistent, yet perception lags behind. The gap between understanding and intuition highlights a fundamental truth. Observation can reveal realities that are beyond the cognitive capacity to fully grasp. Ultimately, the scale of perception becomes a lens for the paradox itself. The planet exists in ways that are measurable and coherent, yet your mind resists their magnitude. Stability, habitability, and coherence operate at dimensions that challenge the framework through which you interpret the cosmos. The universe allows extremes to exist, not only outside expectation, but outside the intuitive bounds of human thought. Observation confronts you with a reality where scale and stability coexist, leaving the mind unsettled even as the data remains precise and reliable. What the data cannot explain. Even with all the measurements, no single existing model predicts all observed parameters simultaneously. The planet's existence is a paradox embedded in data, a real anomaly in a field built on predictability. Planetary science relies on theoretical frameworks that combine gravity, thermodynamics, chemistry, and orbital mechanics. Each framework produces expectations for mass, radius, atmospheric retention, surface conditions, rotation, and internal dynamics. When applied to Earth or similarly sized planets, These models align closely with observation. Predictions match reality, and anomalies are typically resolvable through refinement of parameters or error correction. This planet, however, defies such reconciliation. You observe that every parameter has been measured: mass, radius, surface gravity, atmospheric composition, rotation, tidal heating, internal convection, magnetic field strength, orbital resonance, and thermal flux. Each data set is internally consistent and cross-validated across instruments, time, and methodology. Yet no model, classical or modified, simultaneously accommodates all these extremes. High mass should produce crushing gravity, homogenized atmospheres, suppressed convection, and unstable orbits. Yet all of these processes coexist here in measurable harmony. Consider the interplay of extremes. Atmospheric stratification persists under immense gravity, allowing water vapor and carbon dioxide to remain layered. Surface water endures under pressure that should collapse liquid reservoirs. Internal heat drives geological activity despite the mass that should dampen convection. Magnetic shielding protects the atmosphere even with slow rotational dynamics. Orbital resonance, rotation, and tidal forces operate in a synchronized manner, producing stability rather than chaos. Each process is measurable, yet models predict failure when attempting to account for them simultaneously. The paradox is not subtle. Every refinement of a model that accounts for one feature tends to violate another. Increasing internal pressure to match low-density measurements destabilizes predicted convection patterns. Adjusting tidal models to fit rotation disrupts orbital resonance. Modifying atmospheric models to allow layered chemistry contradicts surface temperature expectations. No combination produces a coherent system in silico that resembles the observed reality. Observation forces a confrontation with the limits of predictive theory. Even error margins cannot reconcile the conflict. You account for observational uncertainty, instrument calibration, and statistical noise. Each parameter retains a sufficient precision to demonstrate that the anomaly is real. Measurement redundancy confirms it. Independent instruments, methods, and epochs yield compatible results. The planet is massive, yet low density, extreme, yet stable, hostile by expectation, yet Earth-like in observable characteristics. Probability alone does not resolve the paradox. You begin to understand the implications. The universe permits configurations that do not neatly fit into established theoretical frameworks. Predictability, the foundation of planetary science, is challenged. This is not a case of incomplete observation, nor is it a fluke of chance. It is an example of a system whose properties are coherent, measurable, and extreme, yet incompatible with existing models. The anomaly is real, persistent, and unavoidable. Ultimately, what the data cannot explain is a reflection of the cosmos itself. Observation is precise, theory is predictive, and yet the planet exists outside the bounds of both. Every measured property contributes to the paradox, and every model adjustment only deepens it. The result is an unsettling truth. The universe contains systems whose behavior is real, observable, and extreme, yet beyond the explanatory reach of current science. The planet is simultaneously known and unknowable, a quiet anomaly that forces recognition of the limits of understanding in a cosmos that does not conform to expectation. A question without comfort. You end each segment with a question that is neither rhetorical nor answerable. How can a world so massive maintain the conditions for life? The data is clear, the contradiction is real, and your assumptions about scale, gravity, and habitability are destabilized by facts alone. You have observed the planet's mass, radius, and density. Each measurement is precise, cross-validated across instruments, and consistent over years of observation. Its surface gravity is high, yet oceans appear to persist. Atmospheric layers remain stratified instead of collapsing under pressure. Magnetic shielding protects the atmosphere despite slow rotation, while tidal heating sustains geological activity. Orbit, rotation, and resonance operate in a delicate harmony. Every measurable parameter should, in isolation, hint at impossibility. Taken together, they constitute a coherent planetary system that defies every model and expectation. The tension becomes almost physical. You understand the principles of planetary formation: accretion, differentiation, and cooling. You know how mass and gravity typically impose limits on atmospheric structure, chemical cycles, and thermal equilibrium. Yet here, all these processes exist simultaneously, each measurable, each functioning, none violating observation. The contradiction is not subtle. It is pervasive. It persists in every dataset, every method, and every observation, and it is observable from light years away. Even in thinking about the star it orbits, the paradox deepens. The energy input falls within a narrow range compatible with liquid water, yet the planet is larger, denser, and more massive than theory would allow for such a thermal balance. The star's variability is smoothed by atmospheric mechanisms, creating a stable environment that should not exist at this scale. Observation, again, contradicts expectation. Every measurable parameter reinforces the anomaly rather than resolving it. You also consider the emergent properties that permit lifelike conditions. Water persists under extreme pressure. The atmosphere remains differentiated. Internal heat drives volcanism and tectonics despite high mass. Orbital resonance moderates tidal stress. Rotation and day length provide moderate diurnal variation. Stability is maintained in a system that, according to models, should be unstable, chaotic, or sterilized. Each feature is individually improbable, yet collectively coherent. The discomfort arises from the quiet certainty of measurement. You cannot dismiss the data as error. You cannot appeal to chance. Multiple instruments, repeated surveys, and independent methodologies all converge. Redundancy confirms the reality of the improbable. The paradox is not a mystery to be solved. It is a fact to be acknowledged. Your intuition is inadequate. Your assumptions about scale and habitability are destabilized. You confront a world whose properties are known with precision, yet remain fundamentally counterintuitive. Even the question itself offers no solace. It cannot be answered comfortably. You cannot reduce the planet to a simplified model, nor can you attribute its coherence to error, coincidence, or anomaly alone. It exists precisely as measured, under conditions that should preclude the emergence of the features that define it. The challenge is not merely scientific. It is perceptual and philosophical. You are forced to recognize that the universe allows realities beyond expectation, and that knowledge, observation, and measurement can confront you with truths that intuition cannot digest. Ultimately, the question remains unresolved. How can a planet of such scale sustain conditions for life? Observation offers no narrative closure. Models provide no reassurance. Every measurement affirms the planet's existence, its stability, and its habitability. Yet each parameter continues to defy expectation. You are left with facts, with certainty, and with a profound unease. The cosmos permits coherence where it should produce chaos, stability where it should impose collapse, and life-compatible conditions where it should not. The data is undeniable, yet the answer remains forever beyond reach.